complementary root locus. I will explain how to draw complementary root locus for both negative feedback and positive feedback systems. For a negative feedback system, the characteristic equation, this is the characteristic equation for a negative feedback system, 1 plus k GSHS equal to 0. And for a positive feedback system, 1 minus k GSHS equal to 0. I have two types of angle criterion. First, I will explain these two types of angle criterion, and then I will explain this root locus and complementary root locus. When k GSHS equal to minus 1, when k GSHS equal to plus 1, then the angle criterion k GSHS equal to 180 degrees or 2q plus 1 180 degrees, odd multiples of 180 degrees. When k GSHS equal to plus 1, it is 0 degrees or 360 degrees or even multiples of 180 degrees. If angle criterion is 180 degrees, then I can draw both root locus and complementary root locus. If the angle criterion is 0 degrees or 360 degrees or even multiples of 180 degrees, I will draw both complementary root locus and root locus. Root locus and complementary root locus. What is root locus? I will define these two terms, root locus and complementary root locus. First, root locus. It is the path taken by the closed loop poles when the gain k is varied from 0 to infinity. So gain k is varied from 0 to infinity. That is, k is positive, right? K is varied from 0 to infinity means k is varied from 0 to some positive values. Complementary root locus. It is the path taken by the closed loop poles when gain k varied from minus infinity to 0. That is, k is varied from minus infinity to 0. That is, k is negative here. We are varying from minus infinity to some negative values up to 0. So these are the definitions of root locus and complementary root locus. Now, these are the angle criterions. We have two types of angle criterions available. One is odd multiples of 180 degrees and another one is even multiples of 180 degrees. Now I will take feedback system, both positive and negative. Negative feedback system and positive feedback system. So this one. This is a negative feedback system. This is the figure. This is the positive feedback system. For a negative feedback system, we have the characteristic equation 1 plus k gs hs equal to 0, right? And from this, k gs hs equal to minus 1, right? For a positive feedback system, 1 minus k gs hs equal to 0. This is the characteristic equation. From this, k gs hs equal to plus 1. For a negative feedback system, now I will draw root locus for this, and I will draw complementary root locus for a negative feedback system. For a positive feedback system also, I will draw both root locus and complementary root locus. Root locus is k is varied from 0 to infinity, and the complementary root locus is k is varied from minus infinity to 0. And here also, root locus means k is varied from 0 to infinity. Complementary root locus, k is varied from minus infinity to 0. For a negative feedback system, k GSHS equal to minus 1. For a positive feedback system, GSHS equal to plus 1. What happens when gain k varied from 0 to infinity? I am drawing a root locus. Second, complementary root locus and complementary root locus. In root locus, the gain k is varied from plus 0 to infinity, right? K is varied from 0 to infinity. That is k is positive and k GSHS equal to minus 1. K is positive. What we will get? Angle criterion. We will get 180 degrees or 2q plus 1, 180 degrees. In complementary root locus, what we are doing? K is varied from minus infinity to 0. What happens? That is k is negative, right? K is negative. What I will do is I will take k equal to minus k1. What happens if I take k equal to minus k1? K equal to minus k1, k is varied from minus infinity to 0. Then what happens? K1. Then k1 is varied from plus infinity to 0. K is varied from minus infinity to 0. K1 is varied from plus infinity to 0. I have k gs hs equal to minus 1, right? I will replace this k by minus k1. Replace this k by minus k1. Minus k1 gs hs equal to minus 1. And then k1 gs hs. What do you get? Plus 1, right? Now, what do you get? K1 plus K1 GSHS equal to plus 1, right? In complementary root locus. K1 GSHS equal to plus 1. What is the angle here? We'll get K1 GSHS. What is the angle? Plus 1 means 0 degrees or 360 degrees or even multiples of 180 degrees. This is the complementary root locus for negative feedback system. What we got? The angle criterion is 0 degrees or 360 degrees or 2q 180 degrees. But here in root locus we got angle criterion is 180 degrees or odd multiples of 180 degrees. So in root locus we got for a negative feedback system. In root locus angle criterion is odd multiples of 180 degrees we got, and in a complementary root locus the angle criterion K1 angle criterion is even multiples of 180 degrees, right? For negative feedback system. For a positive feedback system, k GSHS equal to plus 1. I will draw root locus for this. Root locus means, what is a root locus means? Root locus means gain k is varied from plus 0 to infinity. That is k is positive here, right? When k is positive, k GSHS equal to plus 1 in case of positive feedback system. To calculate angle GSHS, you will get plus 1, that is 0 degrees or 360 degrees or even multiples of 180 degrees. Complementary root locus. In case of complementary root locus, what is the definition of complementary root locus? We are varying the gain k from minus infinity to 0. But we have k gs hs equal to plus 1. What we will do? I will take k equal to minus k1. Then k1 varied from plus infinity to 0, right? If k is varied from minus infinity to 0, then k1 varied from plus infinity to 0. And replace k by minus k1 in the equation. Minus k1 gs hs equal to plus 1. That is k1 gs hs equal to minus 1. Here what do we get? K1 gs hs equal to minus 1. If k1 gs hs equal to minus 1, and the k1 is positive here, right? Now k1 gs hs angle, what do you get? 180 degrees. If it is minus 1, you will get 180 degrees or odd multiples of 180 degrees. a positive feedback system. If it is a root locus, we got K GS HS equal to +1. That is, angle is even multiples of 180 degrees. But if it is a complementary root locus, we got K GS HS equal to -1. That is, angle is odd multiples of 180 degrees. So the summary is, first we have angle criterions. Two types of angle criterions are there, right? One type is odd multiples of 180 degrees and another type is even multiples of 180 degrees. When do we get this odd multiples of 180 degree and even multiples of 180 degree angles? When the system is both positive and negative feedback system. In feedback system, if it is a negative feedback system, we will get two types of angle criterion. If it is a positive feedback system, we will get two types of angle criterion. If it is a negative feedback system, we will get odd multiples of 180 degrees. This one. So in a negative feedback system, if you want to draw complementary root locus, the angle criterion is 2q 180 degrees, even multiples of 180 degrees. In a positive feedback system, if you want to draw root locus, we will get even multiples of 180 degrees. Same in the positive feedback system. If you want to draw complementary root locus, the angle criterion is 2q plus 1 180 degrees, right? Now, so we have four cases, that is negative feedback system, root locus and complementary root locus, positive feedback system, root locus and complementary root locus, right? I will take one of these four, okay? So first I will take negative feedback system and root locus, okay? This we already have known how to draw for a negative feedback system and a root locus. So for this we have certain rules, okay? But what is the angle criterion for this? So first one, this is first one, second, anyway, third and fourth, okay? The first one is a negative feedback system and root locus. We have angle criterion is odd multiples of 180 degrees, right? So the angle criterion GSHS is 180 degrees or odd multiples of 180 degrees. And we are drawing a root locus, right? A root locus means the gain k is varied from 0 to infinity. The gain k is varied from 0 to infinity. That is, k is positive here. So we have certain rules. Those rules we already have known. So this is the negative feedback system. This is the magnitude criterion. Magnitude criterion is 1. Magnitude is 1 and angle criterion. Anyway, already explained this. 90 degrees. Here we are drawing root locus. Root locus means we are drawing the gain. We are varying the gain k from 0 to infinity. That is, when k equal to 0, the root locus starts at open loop pole, and when k equal to infinity, the root locus ends at open loop 0. So when k equal to 0, the path starts at open loop pole. When k equal to infinity, the path ends at open loop 0. The number of root locus branches equal to p if p greater than z, or number of root locus branches equal to z. This is z if z greater than p. So where p and z are number of open loop poles and a number of open loop zeros. And the number of root locus branches approaches to infinity at equal to p minus z if p greater than z, or z minus p if z greater than p. The number of asymptotes equal to p minus z. Both are same. So that is, these number of root locus branches approaches to infinity. How these root locus branches approaches to infinity? These root locus branches approaches to infinity through these asymptotes. So the number of asymptotes equal to p minus z if p greater than z, or z minus p if z greater than p. Where p and z are number of open loop poles and the number of open loop zeros. Center of asymptotes. It is sum of poles minus sum of zeros by number of poles minus number of zeros. angle of asymptotes. Here we got the angle criterion. The angle criterion is, we have taken a negative feedback system, right? Here we have taken negative feedback system and we are drawing a root locus. So for that we have got the angle criterion as odd multiples of 180 degrees. That is why here the angle of asymptotes equal to odd multiples of 180 degrees by p minus z. Okay, where q equal to integer, q equal to 1, 2, 3 and so on, p minus z minus 1. Number of poles minus number of zeros minus 1. So this is derived from angle criterion only. Wherever angles appeared in the rules, those rules are derived from the angle criterion. Angle of departure for poles, complex poles, equal to 180 plus GSHS at S equal to that pole, right? If that pole is minus A plus JB, we have to substitute this S with minus A plus JB in the angle of GSHS. So this is angle of departure. Here 180 is there, right? This 180 is because of this angle criterion. Similarly, angle of arrival theta A for complex zeros equal to 180 minus angle of G of S H of S at that S equal to 0. If that S is equal to minus C plus JD, you have to replace S with minus C plus JD in the angle of GSHS. This 180 came because of the angle criterion, that is odd multiples of 180 degrees. Next, break-in breakover points. So these break-in breakover points are obtained from dk by ds equal to 0. A root locus on real axis. How the root locus exists on real axis. To exist root locus at a point on the real axis, there must be an odd number of poles and zeros right side of that point on the real axis. That is, I will explain this. If I want to know whether the root locus is present at this point, let us say this point, okay? Whether the root locus is present or not, how do you find? Here, to the right of this, to the right of this point, I have one pole, here also one pole, here one zero, total 3, right? So we have 3 is a odd number. So the sum of poles and zeros to the right of this point is 3, that is odd number. So we have a root locus present here. But at this point, to the right of this, one pole and one zero. So the total number is 2. So we don't have root locus. But here only one zero is there to the right of this entire path. So root locus exists. So this also based on the angle criteria. Okay? Odd number of poles and zeros must be present to the right of the point. To exist a root locus at a point on the real axis, there must be an odd number of poles and zeros to the right side of the point on the real axis. So these are certain rules we have when the angle criterion is odd multiples of 180 degrees. These rules are because of the angle criterion is odd multiples of 180 degrees. All these rules. We have taken this first condition, negative feedback system and root locus. Now I will take the second condition, the complementary root locus and negative feedback system. This is the negative feedback system and we are taking the complementary root locus for this. The second case, what we are taking, same negative feedback system, but at this complementary root locus. What is complementary root locus means? A varied from minus infinity to 0. K, Gs, Hs equal to minus 1. K is negative here. That is why we are taking in place of K minus K1. Gs, Hs equal to minus 1. These things I already derived. K1, Gs, Hs equal to plus 1. From this we will get angle criterion plus 0. 0 degrees or 360 degrees. 0 degrees, 360 degrees are even multiples of 180 degrees. This second case, in the second case we have the angle criterion is even multiples of 180 degrees. Then what happens? What happens to the rules? So I will explain the rules of this complementary root locus for a negative feedback system. Because we have got this angle criterion as even multiples of 180 degrees. I will explain all these points, all these rules, whatever the rules explained for root locus plot. So here the magnitude criterion, here this angle criterion is changed to even multiples of 180 degrees. Wherever the angles are there in the rules, those rules are going to be changed. The first point is root locus starts at open loop pole, right? But we are varying k equal to minus infinity to 0, right? If k equal to minus infinity, whether k equal to plus infinity or minus infinity, we will get 0. If k equal to plus 0 or minus 0, we will get pole. Okay? So here this first point will be changed like this. This first point. Here we are varying k equal to minus infinity to 0. Right? If k equal to minus infinity, you will get 0, open loop 0. That is root locus starts at open loop 0. In fact, we are drawing complementary root locus for a negative feedback system. So this complementary root locus for a negative feedback system starts at open loop 0 and the k equal to minus infinity to 0, right? If k equal to 0, we will get pole. That is k equal to 0 is the ending point. So complementary root locus ends at, this is for negative feedback system, right? So this first point is going to be changed like this. So this complementary root locus starts at open loop 0 and ends at open loop pole. 1, 2, 3 points are not going to be changed because these 3 points are not derived based on this angle criteria. These 3 points are not going to change. Next, fourth one. Fourth one also not going to be changed. The fifth one contains angle, right? This angle part, the angle of asymptotes. This angle of asymptotes, the fifth point will be changed like even multiples of 180 degrees by p minus z, right? Where q is same 1, 2, 3 up to p minus z minus 1. And here also angle of departure. So angle of departure also going to be changed. Here we have 180 degrees, but we don't have 180 degrees. In place of 180, we have 0 degrees. 0 plus angle of g of s, h of s at s equal to that pole. So angle of departure of that complex pole equal to 0 plus angle of g of s, h of s at s equal to that pole. Similarly, in place of 180 degrees, angle of arrival, replace 180 by 0 degrees. Right? 0 minus angle of g of s, h of s at s equal to that 0. Eighth point is not going to be changed, dk by ds equal to 0 only. But the ninth point is important. To exist root locus at a point on the real axis, there must be an odd number of poles and zeros to the right side of that point on the real axis. This is for a root locus of a negative feedback system. But for a complementary root locus plot of a negative feedback system, there must exist an even number of poles and zeros to the right side of that point. So in case of odd, in place of odd, replace this odd by even. This is even to the right of that point, right? So take this point here, right? In this point, to the right of this, we have one pole and one zero, right? Odd number of poles and zeros are there. So there exists this path. It is complementary root locus of a negative feedback system. But here in this part, we have 1, 2, 3, odd number. So we don't have any path. That is complementary root locus of negative feedback system doesn't exist. And but here also, here we get path, right? Because to the right of this entire path we have 1, 2, 3, 4, and even number. To the right of this there are no poles and no zeros. So 0 also can be taken as even number in this case. So these are the points going to be changed when the angle criterion is even multiples of 180 degrees. Now this is the second case, and third and fourth are very simple. I have explained these two. The first and second I have explained. Root locus, negative feedback system. Complementary root locus, negative feedback system. Now the positive feedback system and root locus. Third case, positive feedback system and root locus. But the angle criterion we got here. First, I will explain fourth part. Right? In fourth part, we got this one is fourth part. In fourth part, we got complementary root locus of a positive feedback system. The angle criterion is odd multiples of 180 degrees. So to draw this complementary root locus of a positive feedback system, we have to follow the rules of, this is the first part, right? I have already explained these things. So if angle criterion is 180 degrees, how to draw? So we have to follow the rules of first part, that is root locus. So that is angle criterion is 180 degrees. Whatever the points are there, whatever the rules are there, those rules we have to follow for fourth. Next, in third case, root locus of a positive feedback system. This one, root locus of a positive feedback system, we got even multiples of 180 degrees, right? The angle is even multiples of 180 degrees. To draw root locus of a positive feedback system, we have to follow this rule, right? This rule I have already explained. When angle is even multiples of 180 degrees, how the points are going to change, how the rules are going to be changed. Those rules we have to follow. Now I will explain a question that is given, right? So this is the question. I will explain the question and I will solve it in the next lecture. The transfer function of a closed loop system is, this is the transfer function. It is not open loop transfer function. Transfer function means closed loop transfer function, where k is the forward path gain. Okay. The root locus plot of the system. Here he mentioned root locus, right? Not complementary root locus. He mentioned root locus. Root locus means what we have to do. This k is varied from 0 to infinity, right? It is not complementary root locus. It is root locus only. So what is the characteristic equation he has given here? S square plus 3 minus k into s plus 1 equal to 0, right? This I will write as s square plus 3 minus k s plus 1 equal to 0. S square plus 3s minus ks plus 1 equal to 0. 3s. Now 1 s square plus 3s plus 1. Take this as a common. Next you will get 1 minus ks by s square plus 3s plus 1 equal to 0, right? From this 1 minus k into s by s square plus 3s plus 1 equal to 0. This is 1 minus k gs hs equal to 0. Compare this with this equation. So where gs hs equal to s by s square plus 3s plus 1. From this open loop poles, minus 3 plus or minus b square minus 4ac by 2, root 5 by 2, right? These are open loop poles. And open loop 0 is also there. S equal to 0 is a open loop 0. This one is 1 minus k gs hs equal to 0. From this k gs hs equal to 1 is positive, right? Now k gs hs equal to 1. But what is the question? We have to draw the root locus plot of the system, right? So what is the root locus? Root locus, the definition is, root locus is k varied from 0 to infinity. That is, here the k is positive. If k is positive, what do you get the angle criterion? Angle criterion will get plus 360 degrees or 0 degrees or even multiples of 180 degrees, right? So in case of even multiples of 180 degrees, the rules are going to be changed. So I will plot this in the next lecture.